If you watch a person learning, say, a new video game, they don't usually spend hours just randomly pressing buttons.
No, not at all.
They look at the objects, right? They
Mhm.
sort of intuit the rules, how things move.
Mm-hmm.
And they often master the basics, pretty fast, sometimes in minutes.
That's human learning. Very data efficient.
Exactly, data efficiency. Now, contrast that with state-of-the-art deep reinforcement learning, DRL.
Big difference there?
Huge difference. These systems often need hundreds of thousands, maybe even millions of interactions.
Yeah, just to figure out the basic physics of the game world.
It's this massive gap in learning speed, and that's arguably, I think, one of the biggest efficiency hurdles for modern AI.
It really is.
But what if we could build something that merges that human advantage, those core intuitions about the world, with the raw power of modern computing?
Well, that's pretty much the driving idea behind AXIOM.
AKMM, right. Active expanding inference with object-centric models. Quite a name.
It is. And the sources we're looking at today position AXIOM as, well, a significant step towards bridging that exact gap you mentioned.
Okay.
It cleverly combines Bayesian methods, specifically something called active inference, with these very expressive object-centric models.
Right.
So our mission for this deep dive is really to unpack how AXIOM manages to get, state-of-the-art results, but in these really low data situations.
And we're talking really low data here.
We are, specifically the 10,000 interaction step mark. And crucially, it does this using an approach that's gradient-free, transparent, and interpretable.
Okay, gradient-free and interpretable. That sounds very different from standard DRL. So let's start with the basics. Why is current DRL so incredibly data hungry? What's the core issue?
Well, fundamentally, it often boils down to a lack of, let's say, built-in structure.
Okay.
So first, obviously, there's the huge amount of data needed, like you said.
Mm-hmm.
Second, to learn stably, DRL typically relies on these massive replay buffers, essentially big digital memories storing past experiences.
Which eats up memory and computation.
Exactly. The resource sinks. And maybe most critically, these methods often lack what you might call structured exploration.
Structured exploration.
Yeah, they tend to explore kind of randomly, or just focus on maximizing the immediate reward signal they get back. They don't have a principled way to, say, seek out information specifically to improve their understanding of how the world works.
Okay, so they're just sort of optimizing for points rather than understanding.
In a way, yes. Which brings us to how humans do it differently. We use these core priors.
Core priors. Right, so if DRL learns everything from scratch, what are these priors that humans seem to rely on?
Think of them as fundamental assumptions, or maybe hyperpriors, that our brains use to sort of scaffold learning and perception right from the get-go.
Like built-in knowledge.
Kind of. Innate assumptions about basic physics, perhaps. We intuitively understand that objects tend to move smoothly.
Yeah, they don't just teleport.
Exactly. And that, for an object's path to change significantly, something usually needs to happen, an external force, a collision, a push.
Makes sense.
And this basic understanding lets us predict movement and figure out cause and effect relationships almost instantly. DRL, on the other hand, often just sees a confusing blast of changing pixels without that foundational structure.
So AI needs that structure. And you mentioned AXIOM uses active inference to get there. How does that framework help integrate this kind of prior knowledge?
Active inference is quite interesting. It's a Bayesian framework, which means it deals with probabilities and beliefs.
Okay.
But it's uniquely suited for combining prior knowledge, like those core physics assumptions, with the incoming stream of sensory data, like pixels from a game.
And it quantifies uncertainty.
Precisely. Unlike standard learning, it doesn't just build a model of the world, it also constantly tracks how uncertain it is about its own beliefs and predictions.
So it knows what it doesn't know.
Exactly. And that awareness lets it prioritize actions that are most likely to reduce its uncertainty to gather information actively. It's a process that many believe aligns quite closely with how our own minds work, how humans explore and learn.
Now, you mentioned earlier that previous active inference models were often kind of custom built, like designed for one specific task.
Yeah, that was often a limitation. They could be quite powerful, but sometimes very bespoke, as the source material puts it. Hard to generalize.
So how does AXIOM get around that? How does it achieve broader applicability?
It actually narrows the focus of the priors, but makes them more fundamental. Instead of encoding rules for, say, Pong specifically, AXIOM uses a really minimal but powerful set of priors about object-centric dynamics.
Object-centric, so things like position, movement.
Exactly. General concepts.
Hmm.
Position, identity, velocity, basic interaction rules, not rules tied to one specific game environment.
Hmm.
By building on these object-focused priors, AXIOM gets the benefits of Bayesian efficiency and that interpretability we talked about, while still being flexible enough to tackle different kinds of challenges across various environments.
And this focus on object priors leads directly to a major architectural advantage: efficiency. Specifically, being gradient-free.
That's the key payoff, really. AXIOM learns sequentially. It processes one frame of the game at a time.
One frame at a time.
Yep, using what's called variational Bayesian updating. You can picture it as constantly tweaking its internal beliefs and its certainty level with every single new piece of visual information it gets.
Wow.
And the crucial consequence is that this strategy completely eliminates the need for those huge replay buffers we discussed.
Okay.
And it also bypasses the incredibly computationally expensive process of gradient-based optimization that's central to most DRL. It's true online adaptation learning continuously, right, as things happen.
That sounds incredibly lean, computationally speaking. But if it's just learning frame by frame, how does it build up a complex understanding? How does it, expand its knowledge without that typical deep learning approach?
Well, that's where the expanding part of the name comes in.
Yeah.
AXIOM uses a dynamic mixture architecture.
Mixture architecture.
Yes. It allows for very fast structure learning. So imagine some new data comes in, maybe a new type of object appears that the current model just can't explain well.
Okay.
AXIOM dynamically expands its model online by adding new components, new potential explanations to account for this surprising data.
So it grows its model on the fly.
It does, but importantly, it also cleans up after itself. To stop the model getting too complex or overfitting to noisy data, it periodically refines itself.
Refine.
It merges components that seem redundant or are explaining basically the same thing.
Yeah.
This uses a technique called Bayesian model reduction.
Yeah.
It's like constantly tidying up its internal map of the world to keep it efficient and generalizable.
Okay, that makes sense. Expanding when needed, simplifying when possible. It's keeping its mental map neat. Let's dive into that map then, the world model itself. AXIOM sees the world as made up of objects, right? Each with its own model components.
Exactly. It's fundamentally object-centric. There are 4 key mixture models that work together to create this view, starting right from the visual input.
All right, component one.
Component 1 is the slot mixture model, or SMM. Think of this as the perception layer. It takes the raw input, those 210 by 160 color frames from the game, and it parses those pixels into distinct object-centric representations. So it calls these slots. It can handle up to 32 of them.
And what does it extract for each slot?
Continuous features, things like position, color, and shape attributes for each potential object or slot it identifies. It's basically carving up the visual scene into manageable pieces.
Okay, so the SMM is like the eye, breaking down the scene into visual parts. Once it has these parts, what's next?
Next up is the Identity Mixture Model, or IMM.
Right.
This takes those continuous features from the SMM, specifically color and shape, and it infers a discrete identity code for each slot. Basically, it tries to figure out the type of object it's seeing.
Why is that important?
It's absolutely vital for generalization. It allows AXIOM to recognize that, say, this red ball is the same kind of thing as that blue ball it saw earlier, even if the color is different.
Ah, so it can reuse knowledge.
Precisely. It can apply the same learner dynamics model, the same rules of behavior, across different instances of the same object type. Big efficiency win.
Okay, so we've seen the object, we've identified its type, now we need to know how it moves. That must be the next model.
That takes us to the Transition Mixture Model, or TMM. This one focuses purely on the dynamics, the movement of a single object at a time.
How does it model movement?
It discovers these reusable motion prototypes. Think of basic patterns like falling straight down, sliding sideways, or bouncing. It models these by defining an object's trajectory as a series of simple, piecewise linear functions based on its own current state.
Piecewise linear, like straight lines connected together.
Pretty much. Simple, but effective for minigame physics. And the power here is that these learned motion prototypes, falling, bouncing, etc., are shared and applied across all objects in the scene that the IMM has identified.
Got it. So that covers individual object movement. But, games are usually about interactions, objects hitting each other, scoring points, hitting walls. Where does AXIOM learn about cause and effect?
That's the crucial final piece.
Yeah.
The Recurrent Mixture Model, or RMM. This is where the relational intelligence lies.
Okay.
It specifically models those sparse but important object interactions. Think collisions, basically.
How does it link actions to outcomes?
It connects various features together, It looks at continuous features like, say, the distance to the nearest other object,
Uh-huh.
and it links those with discrete features, like which motion prototype the TMM is currently using, what action the agent just took, and critically, the reward signal it received.
Ah, so this is where it learns, if I hit the ball with the paddle here, I get points.
Exactly. This RMM is where AXIOM figures out those causal links.
Yeah.
If I do action X when I'm near object Y and my state is Z, then outcome W is likely to happen. It's learning the rules of interaction.
The whole four-part structure sounds really well thought out, comprehensive. But the big question, of course, is performance. Does this lean, gradient-free architecture actually hold up against the big DRL system?
That's what the researchers tested, and they used a new benchmark suite called GameWorld 10K.
GameWorld 10K, why create a whole new benchmark? Weren't existing ones good enough?
Well, most of the established benchmarks, like Atari maybe, they often emphasize really complex, long-horizon planning problems, and they typically require millions, even hundreds of millions, of interaction steps.
Right.
The sources here specifically needed a way to test rapid learning, fast adaptation. So GameWorld 10K includes 10 diverse games names like 88, Bounce, Gold, Explode. They're visually quite simple but focus on object interaction.
And the key
A strict limit. Only 10,000 interaction steps allowed. Max. These are games a human could likely figure out very quickly, so it forces the AI to be incredibly efficient.
Okay, the stage is set for a showdown. 10,000 steps. How did AXIM do?
The results were, well, pretty remarkable according to the sources.
Yeah.
AXIM achieved either higher, or at least statistically comparable, average cumulative reward compared to two very strong state-of-the-art DRL baselines. Those were BVF and the well-known Dreamer V3.
Higher or on par with Dreamer V3 in every game?
In every single one of the 10 GameWorld 10K games within that tight 10,000 step budget.
Wow. Okay, let's really underline the efficiency difference here, because it's not just about the final score, right? It's the speed.
Absolutely. AXIM often converged much, much faster. In many cases, it reached most of its final reward score within the first 5,000 steps, sometimes even sooner.
Half the allowed time.
Yeah.
But the parameter count. That's the number that really jumped out at me from the sources.
Oh, yeah. It's orders of magnitude different. AXIOM, with its gradient-free updating, operates using a model size of only about 0.3 to 1.6 million parameters, depending on the specific game complexity.
Okay, 0.3 to 1.6 million and Dreamer V3.
Dreamer V3, one of the leading systems it was compared against, uses around 420 million parameters.
Wait, did you say 420 million?
420 million, yes.
Compared to Max, 1.6 million for AXIOM. That's not just an improvement, that's a completely different scale of complexity. How is that even possible?
It really highlights the power of having the right kind of built-in structural knowledge.
Core priors.
Exactly.
Yeah.
Because AXIOM starts with those object-centric priors, it doesn't need to learn the very concept of an object, or that objects generally move smoothly from raw pixels. The amount of learning required, the complexity needed to generalize, is just drastically reduced. It builds upon those foundations.
Which leads perfectly into the final major point.
Yeah.
This idea of the white box advantage. DRL models are often described as black boxes, right? You get an output, but it's hard to know why.
Very much so. Debugging them or understanding their failures can be incredibly difficult.
But with AXIOM, the claim is that you can actually look inside and understand its reasoning.
That's one of the most compelling aspects, yes. Because the model is built from these meaningful components. The learned features for shape, color, position, those distinct motion modes from the TMM, they are actually human-readable. You can, quite literally, inspect the agent's learned beliefs about the world.
Can you give an example of that?
Sure. The sources describe visualizing the clusters learned by the RMM, the interaction model, specifically looking at clusters associated with rewards or punishments.
Okay.
In the Impact game, which is like a breakout or Pong variant, they found a distinct cluster of beliefs that the system consistently associated with failure, with punishment.
And where was this cluster?
When they plotted it spatially, this failure cluster, they colored it, red, appeared clearly right at the bottom edge of the screen where the paddle would miss the ball.
So AXIOM explicitly learned ball reaching this bottom area means I lose a point.
Essentially, yes. Its learned belief was transparent and corresponded directly to the game mechanics. If the ball gets to this spatial location, I expect a punishment because it means the paddle missed. That's interpretable causal knowledge, not just correlations in pixels.
And this interpretable knowledge is kept efficient using that Bayesian model reduction, the BMR you mentioned earlier, the spring cleaning.
Exactly. BMR plays a crucial role in maintaining both performance and interpretability. especially for generalization.
How so?
It actively looks for and merges those dynamics, clusters in the TMM or RMM, that seem to be describing very similar underlying events or physics. This prevents redundancy and keeps the model complexity low.
So it helps it realize, say, bouncing off the top wall follows the same rule as bouncing off the sidewall.
Precisely. It helps AXIOM understand the general principle of bouncing, rather than learning separate, specific rules for every possible bounce scenario. This merging process was found to be particularly important for robustness in games involving a lot of 2D movement, like Gold and Hunt.
And they directly tested this robustness, right? By messing with the game environment midway through learning.
They did. At step 5000, after the model had learned quite a bit, they introduced perturbations.
What happened when they changed object shapes?
AXIOM was remarkably resilient, it's barely dipped. The identity model, the IMM, correctly inferred the object's underlying type using other features, like maybe movement patterns or size, even when the exact shape changed.
Okay, shape wasn't critical for identity. What about changing colors?
Color changes did cause a temporary drop in performance, but AXIOM recovered quite rapidly.
Wow.
It essentially just had to relearn the mapping. It kept its existing learned dynamics models intact, but quickly reassigned the new visual colors it was seeing to those old established object identities and behaviors. The core structural understanding of how this type of object moves and interacts remains stable.
And this leads to the ultimate demonstration of the white box benefit, the color remapping trick they described.
Yes, that was a really neat illustration, because the model's features, like color and shape used by the IMM, are explicit and understandable.
Yeah.
The researchers could actually intervene manually without any retraining. They just told the IMM, okay, ignore color for now, just use shape to figure out the object's identity.
And the result?
Instant performance recovery. By directly injecting that bit of structural guidance overriding the temporarily confused color feature, they completely rescue the agent's performance.
Which you absolutely couldn't do easily with a typical black box DRL model.
Not without potentially massive retraining cycles, no. It really proves the value of having a transparent model structure where you can diagnose and even potentially fix problems based on understanding its internal workings.
Okay, so stepping back from all these details, what's the big picture takeaway from AXIOM?
I think the core message is pretty clear. These structured Bayesian approaches, especially when combined with intuitive, object-centric representations, offer a really powerful and potentially much more scalable path towards AI that is both highly data efficient and inherently interpretable.
Yeah.
AXIOM really demonstrates a practical way to bridge that gap we started with, combining the efficiency you get from having explicit knowledge structures with the expressive learning capabilities we see in modern AI.
It feels like a fundamentally different, maybe more human-like approach to learning. Really impressive efficiency. But the sources do point out a key constraint, and it's something important for you, the listener, to think about.
Its reliance on priors.
Exactly. AXIOM's power, its incredible efficiency, hinges entirely on those core priors, those fundamental ideas about objects, interactions, smooth movement being carefully chosen and engineered into the system by humans.
They have to be designed up front.
Right. Which leaves us with a really provocative question to mull over. What happens next? What would it take for an AI system to not just use these fundamental organizational principles, but to actually discover them automatically, purely from observing the raw data itself, without humans needing to pre-specify them? That's the frontier to think about.